Okay, so continuing on our discussion of electron configurations, that is the ground state electron configurations, the most stable arrangement of electrons within atoms, we're going to use our periodic table as a guide. And it's very useful for us to remember that the way the periodic table is arranged will help us predict the arrangement of the electrons in most cases. And again, there are some exceptions to this sort of simple strategy, but we really are not going to worry about those exceptions, and we're going to focus on those examples that follow this rule. And really what this is most useful for is for our main group elements, that is our S block and P block elements. And yes, we will from time to time use this to describe our D block and F block elements, but it's most useful for our representative elements. Okay, so one of the peculiarities that we saw last time is that when we go from 3s to 3p, when we continue down, for example, to go to potassium, we go to our 4s orbitals before our 3d orbitals. Okay, and it turns out that for most elements, these 3d orbitals are higher in energy than the 4s. And this indeed was predicted by the Bohr model of the atom. Okay, but again, we're just going to use this model to predict the electron configuration, and this is going to help us understand something about the chemistry and some of the periodic trends that we observe with different atoms. So let's come back here and let's do the configuration for sodium. So sodium has 11 electrons. So we're going to begin with hydrogen and then helium, right? So those are our 1s orbitals. We're going to fill our 1s orbital coming to helium. Then we're going to come down to our 2s orbitals and fill those up. So we have 2s2. Again, remember this superscript indicates the number of electrons, and this tells us the type. So we have 2 electrons in the 1s orbital, 2 electrons in the 2s orbital. Then we are going to put, we're going to put electrons in our 2p orbitals, so that we have a total of 3p orbitals, so that's a total of 6 electrons. This brings us to neon. And then coming over here down to our 3s level, we have 1 more electron. Again, we just use the periodic table as a guide, and that way we don't really even have to count our electrons. We just need to make sure that whenever we're filling up our s orbitals, the s orbitals hold 2 electrons. When we go to the p orbitals, there are 3 p orbitals, each holding 2, for a total of 6 electrons. Okay, and this is what we call our electron configuration. This is what I call the full electron configuration for sodium, or really more correctly, the full ground state electron configuration for sodium. Okay, now you may have noticed already that every time we do the electron configuration for any element, we always start at the same place. That is, we start with the 1s orbital, and we fill that 1s orbital most of the time, and then the 2s orbital, and then the 3s orbital, etc., etc. So we always follow the same strategy. And what this leads to is that we can sort of expect that the orbital configurations are going to be the same for all of the elements, right? And so we can write these in a condensed format, okay? And the way that we do this, and it's sort of it introduces an important idea, is that we will write the nearest noble gas configuration and then only write those electrons that are most important to us. That is the outermost electrons, or what we call the valence electrons. So for example, in sodium here, we see that all of these electrons are what we call the core electrons, right? These electrons all correspond to right here, right? They correspond to the electron configuration of neon. And remember in class we had said that there's something special about noble gas configurations, okay? And we represent this notion of the importance of noble gas configurations in terms of their stability by writing a condensed configuration which represents the core electrons, those that are typically not involved in chemical properties, as the noble gas configuration. Okay, so for sodium, our 1s2, 2s2, 2p6 all correspond to our noble gas configuration. These are our core electrons. And then we put those in a square bracket around the symbol for that noble gas. And then outside of those, we write the ones that are interesting to us. And these are what we call the valence electrons. And so in the case of sodium, we would see that we have a single valence electron. Okay? And so this condensed configuration really emphasizes an important piece of insight that we get from these electron arrangements, and that is we have a distinction between the core electrons that are always of a noble gas configuration and those outside of that core that are going to be responsible for the particular chemical properties of that element that we call the valence. So the fact that sodium has a single valence electrons really helps us explain a lot about the chemical properties of sodium that we're going to talk about in a little while. Okay, so this valence shell is the highest energy occupied ground state orbital. Okay, and we call it the valence shell or the valence electrons. So for hydrogen and helium, this is that n equals 1 shell, that n equals 1 orbital. For the next period, these are all of the electrons in all of the orbitals that contain n equals 2 orbitals or shells. Okay, and let me give you a couple more examples here. Okay, so let's do magnesium. Okay, we look at magnesium, and that is in our second period, third period. This is element number 12. Okay, magnesium has a configuration of 1s2. Follow along on your periodic table if you can. 2s2. 2p6, again this brings us to neon, then 3s2. Okay, and so our condensed configuration would be the configuration of neon and then 3s2. And so magnesium has 2 valence electrons. These are the electrons outside of that core. Let's do a couple more quick examples here. I would like to do carbon. Okay, carbon has a configuration. We begin in the same place. 1s2, 2s2, then 2p2. Okay, for a total of 6 electrons here. Now, when we look at carbon, so up here, magnesium had 2 valence electrons. We saw that sodium had 1. In the case of carbon now, our core electrons are these. So our condensed configuration for carbon would be helium and then 2s2, 2p6. And so for carbon, let me make a little bit more space here. Carbon will have a total, oops, I'm sorry, not 2p6, 2p2. Carbon will have a total of 4 valence electrons. Okay, again, it's all of the electrons outside of the core. And let's just do one more. Let's do silicon. Okay, so silicon, element number 14. We're going to begin with the same place, 1s2, 2s2, 2p6, 3s2, and then we're going to come to the 3p's. So I'm going to write the condensed formula starting at the previous noble gas, which would be neon. No, you know what? Let's do the whole thing. 1s2, 2s2, 2p6, 3s2, again, following along on your periodic table, and then 3p2. Writing our condensed configuration, this would start with neon at element number 10, then we go to 3s2 and 3p2. And we look at this configuration, and again we call the valence electrons those that are outside of this core. So just like carbon, silicon also has 4 valence electrons. And it turns out that the chemistry of silicon is very similar to the chemistry of carbon, and the reason for that is because they have the same number and the same arrangement of valence electrons. And we'll build upon this idea as we move forward.